Okay, tonight we're going to look at physical networks, and I don't really like the way you will learn. We're going to talk about physical networking terminology, the functions of network infrastructure devices, copper media and connectors, and then the optical media and connectors. So physical networks is the topic here. Module A. Connecting technologies. We're going to go through the signals, the different kinds of signals that we have with these things, the difference between a bit rate and a baud rate. Bit rate basically is how many bits per second you get. Baud rate is the number of changes, and we can get a higher bit rate than baud rate by the way we do compression with these things. About types of signal multiplexing. Multiplexing, if you've got cable TV and cable modem, you're doing multiplexing already. Ethernet is everywhere. We call it Ethernet, and we'll continue to call it Ethernet. But what really makes an Ethernet is it uses the CSMA-CD, carrier sense multiple access, collision detection, the kind of the thing that we talked about, for media access, and it's a bus topology. What we use today in most cases is called switched Ethernet or fast Ethernet in order to do that. It works a little bit different. Some of the older switches use the CSMA-CD, although it's probably unnecessary, and we'll look at a little bit later how that switch gets its MAC addresses so it knows which port to send the information out of. Used in telecommunications, we're going to use it in some WAN technologies now. Point-to-point protocol over Ethernet. Point-to-point protocol, if you remember, was a wide area network protocol. Ethernet was a local area network protocol. What we do when we do the PPPoE, point-to-point protocol over Ethernet, is encapsulate one protocol within the other. DSL, Ethernet, and this is something that I think is kind of interesting. It was designed in the 1970s, not that it was designed ever, by Xerox. And Xerox had to make a decision of whether they were going to go with the duplicating business or the networking business. And they went with the copier business. And the networking, the connectivity, went elsewhere. They could have been a primary player in this, but they decided to go with duplicating instead. Standardized in the 80s by the IEEE with the 802.3 standard. The 802 standards, there are a number of them. The LAN technology, 802.3 is Ethernet, 802.5 is token ring, 802.11 is wireless. So those are the same. The Institute of Electrical and Electronic Engineers is IEEE. Ethernet operates at layer 1 and layer 2. After we get above layer 2, once we get to the network layer 2, the IP, and the IP is going to be the protocol that we're going to use here. There are others that have been used in the past. IPX is one that you'll see in the literature, which was the old protocol that NetWare used in NetWare 3, and they're on like IPX went away in probably the early 2000s. Even NetWare shifted to IP. They shifted to a proprietary IP, but they shifted to IP. So it operates at layer 1 and layer 2. The original was 10 base 5, and now we'll get over 40 gigabytes. We haven't really talked about those speeds yet, and let's do that real quick before, so that when we see these terms, they kind of make a little bit of sense, and we'll revisit a lot of them. If we have 10, and we're going to talk about baseband and broadband here in a few minutes. 10 base 5. The 10 is the speed, which is, in this case, is 10 megabits per second. The base is baseband, which is different from broadband, which baseband means that it's a single frequency, and that single frequency gets all of the data. And the 5 here is the length, how far it can go. And in this case, 5 is 500 meters. What we're going to see mostly is going to be 100 base T or 100 base TX, which is going to be 100 megabits per second baseband, and T is going to be twisted pair, or 1,000 base for the gigabit, 1,000 base T. 1,000 megabits per second, gigabit per second for these things. But when you see this 10 base, and that's what those numbers and letters stand for. Now, how fast are we going? So we started out in wired with 10 megabits per second, and we had 10 base 5 and then 10 base 2. 10 base 5 they used to call, and that's one that was before me. We had thin net that was called thick net, which a lot of people say is like a frozen water hose. Big coaxial cable. Thin net, not so much. It's a much thinner, but it was 10 base 2. And believe it or not, the 2 meant not 200 meters, but 180 meters. And these are all in meters and not in feet when you do these things. And that's when you're doing the questions, be sure that it says meters if you get that question and not feet, because sometimes they'll throw things in that shouldn't be there. So a modem, modulator, demodulator, this is something that's going to be operating at layer 1. Turn the data into a signal to send across the media. And the modem, the true modem, we talk about cable modem. Cable modem does some interpretation for us. What a true modem does, a dial-up modem does, is takes the digital signal and changes it into an analog signal so that it can go over the phone lines. The physical transmission is going to be analog. Signal is going to be encoded for transmission, and I want to, when we get near the end of this, there's a little video that I want to watch that you can actually, the guy goes through and he has an oscilloscope hooked up to a network cable, and you can actually see what the signal looks like on the simplest encoding is a single binary signal. Digital baseband or line coding is used, and these things are used in Ethernet. Voltage or light is on or off. It's a on or off, and that's the advantage. And in the copper with light, it's going to be the light on, light off. In copper, it's going to be a positive, actually going from a negative to a positive voltage, or a positive to a negative voltage for a zero. So we use the encoding methods in order to represent the ones or zeros. These are some of the terms. I try to put pictures in here so that hopefully some of the terms make sense. The data is combined with a carrier signal. Carrier signal is a constantly changing up and down analog signal, or a signal that we're going to use. A carrier signal would look something like that. Constantly changing. We're going to combine the data with the carrier signal. It's modulated, modified, or modulated by the transmitter, and create an analog signal with these things. The receiver is going to be demodulated, and we code and decode with the modem. Most of the signals we use are actually going to be analog when we do these things. And with the different types of modulation, amplitude modulation, how high is it? How strong is the signal? And in this thing, the amplitude modulation, we have nothing going here, and then we have some voltages, the up and down, the voltages from probably like a -1 to a +1 volt. And that's going to represent a 1. And then we go back to the steady state, going to represent a series of zeros. It knows how many of these things to put in because of the timing that goes on. It expects a signal every so many nanoseconds to do these things. So the amplitude modulation, we actually have something here. And that's what's going to represent to the network the ones and the zeros that we're talking about. Phase modulation here, and the phase modulation is when the signal starts. If it starts here and then it starts here, these are going to be out of phase signals. So we change the phase of these things, and here's going to be the phase change, and that's going to be the 1, and here's going to be another phase change. The leading edge and the falling edge of these things are going to be the phase changes. So zeros and ones. And then the other one is frequency modulation. How many changes per second do we have in the carrier signal? So we have a carrier signal here, and then it becomes really, really rapid, much more rapid, represents the 1, gets spread out again, it's going to represent the 0. So the frequency change, frequency modulation, phase modulation, and amplitude modulation are the types of signaling that we're going to use. And then we kind of talked about this a little bit already, the signaling. We have baseband, broadband. Baseband, a transmission technique that one signal requires the entire bandwidth of the channel to send data. We get here into what's bandwidth, because you and I in the networking, when we talk networking, we're usually talking about bandwidth really is data rate. What's the megabits per second? I got a 200 megabits per second bandwidth. What a bandwidth really is the difference between the low and the high frequency in one of these things. So what that's saying is that the baseband requires all of the frequency, all of the carrier signal in order. Baseband is used in digital transmission. Broadband, transmission that many signals with multiple frequencies can be transmitted over. And we'll say this is our piece of coax, big piece of coax, right? And we have cable TV. We have all of the different channels in here, a little bit different frequencies going on this same piece of media that is going to allow us to put multiple channels on the same piece of media. And what we do is we have cable, the TV channels are on frequencies, and then the cable modem are going to be on the different frequencies to do these things. So we have them, or if you've got DSL, your voice is going to be on one frequency, and then you actually have to put filters on the phones, and the data signal is going to be at a different frequency on it. So we have baseband is a single transmission, takes everything. Broadband has lots of different signals on it. So what I'm trying to represent here, and it says 3 channels in a broadband transmission here, and that's the one out of the book, I think. But over here we have baseband interleaves with the TDM, the data voice video. The baseband, everything, or the baseband signal gets the entire bandwidth. Down here we have data gets part of it, voice gets part of it, video gets part of it. So we have broadband, multiple signals on the same piece of media. Broadband, a single signal on those things. It's going to be data. You may say, well, I have an IP phone. Well, you may have an IP phone, but it's still going to be data. It's still going to be represented as data on that baseband. Bit rate versus bandwidth. And this is back to what we think of as bandwidth, which is really probably more technically called signal rate or data rate to do these things. So the bandwidth, the amount of data a network can carry. Bandwidth can mean the frequency range like we talked about. And if you have radio stations, if anybody listens to radio stations anymore, they are assigned a frequency band, and if we're, FM 96.3, it's going to be the center frequency of that range. And then they do all of the signaling within this range that they can't have leak over to another one, because we're going to have another station right next to it, and you don't want to leak one signal into the other. So it can mean that. What we normally think about it, though, is the amount of data that we can carry. And the more proper term is the bit rate, the number of bits carried per second. And that's what we say. We say I got a 200 megabits per second, bits per second. So the data rate, we don't say that that's our bandwidth. We call it bandwidth, but we don't call it bandwidth when we talk about it. We talk about bits per second. We have a gross bit rate and a net bit rate. The net bit rate is going to be the throughput, how much useful data actually goes through those things. So, I mean, I can have the 200 megabits per second, but I may not be able to actually get that data rate because there's going to be some overhead, some control stuff that goes on, and we're going to call this good put, or the throughput that we actually get is going to be good put, the stuff that we use. The baud rate is the number of symbols, and symbols are just tones. You may or may not have ever heard an analog modem start up, and it sounds like just a bunch of noise. Once you get on and you pick up the phone inadvertently while the signal's going on, and it's tones. The phone system is tones that do these things. So the tones per second is going to be the baud rate. what happens is the number of changes per second is baud rate. The way that we get more data is that we're going to represent more than one bit at a time in order to do that. If we had, maybe a 0, 1, 2, 3 here, 0, we could represent them, and being in the binary, the first bit is 1 and the second bit is 2. So 0, 0 would be a 1, or maybe a 0. Actually, 0, 0 would be a 0. A 0, 1, 1, 0, and 1, 1. So we would have 0, 1, 2, and 3 represented by a single change or a single signal, but we're representing more than one bit with that signal. So baud rate, changes per second, bit rate is how much data we're actually sending. Multiplexing, and active networks do carry large amounts of data. Your network at home carries large amounts of data. Those of you who are at the facility at Jacksonville, you're carrying large amounts of data out of here. Different things. We got voice in here, we got some video, we got all this stuff going on. You got data going in and out for different things. But what we do is multiplex. By multiplexing, we're going to put multiple signals on the same piece of media to get from one to the other. We have a multiplexer and a demultiplexer. The one at the top is supposed to be showing that in a multiplexer, we put A on here, conversation A on here, and then after we get A, we go to B, and then we put conversation B on here. It would go across, and then conversation C, and then D, and then E. And if we had more, we could start over again in order to do that. Different messages into a single stream is multiplexing. A number of different ways to do that. And down here we see signal 1 goes over, signal 2 goes over, signal 3 goes over. They get access to the media. And when we get to the other end, we actually have signal 1, 2, and 3 that's going into the data stream to go from point A to point B. So multiplexing, when we put multiple conversations on the same. Types of multiplexing, and I got some images here in just a minute. Space division multiplexing, multiple parallel physical connectors to transmit the data streams. Frequency division multiplexing, different carrier signals operating at different frequencies to transmit the different streams. And then time division multiplexing breaks the conversation up into separate frames called time slots, and the controller assigns time slots to the devices. So what do they look like? The top one there, space division, multiple signals or multiple lines with signals on it. The frequency division, different frequency, signal ones at 40K, 50K, 60, 70, 80, different signals at different frequencies to do these things. And then time division multiplexing, each time slot. And the time division multiplexing is kind of like maybe you're going to go ride the roller coaster and you got the cars come up. Each car could represent a time slot. So, the first row gets filled, the second row, third row on down the line until each of the individuals is in their own seat in their own time slot to get onto the ride. So, kind of an odd maybe thought of the way this looks. So we now jump into the data link layer, and then the data link layer itself is where the LLC, the logical link control, and the media access control is. It's where the MAC address is going to be. And the first one there says the physical layer is bits. It's 1 and 0s. It's just data going across. It has no concept of address at all, and no media sharing concept. It doesn't care. You just the transport layer or the data link layer sends it the information, breaks it up into the 1s and 0s, and it sends it on its merry way. But we know in order to deliver the information to the proper location, we got to have an address of some kind. And that's where the data link layer comes in. We also just can't have chaos, and you've probably seen that on highways or parking lots where everybody's just going everywhere and it's a mess. Or maybe bumper cars would be a better at the state fair would be a better concept of disorganization of these things. But media access control, and we've talked about it. How do we get access to the media? And we had the two. The one with the Ethernet was the carrier sense multiple access collision detection, and then we had token ring, which when we had the token we could have access. Different ways we have now at the logical link after we get out of the physical and the signaling, and all this signaling stuff, going the wrong direction, all of this are things that are going to happen at layer 1. The signaling takes place there. And that was what we said. The media is really not part of it, but the signaling, the way we put the signal, the voltages that we use, the connectors that we use, the type of media that we use are all defined there. But the media itself is just there. It's the conduit. Now we move up. We have to determine where it's going and who gets to use it, who gets to get onto the highway, who gets to get onto the data link. So the objective of a network is communication. We all want to get information. We have the two sublayers at the data link layer. The MAC creates frames and negotiates multiple access. And the frames we looked at a little bit, and we'll look at frames again. The frames don't really have all that much in it. It's going to come up again. It's got a repeating ones and zeros, a sync signal, start a frame, the destination MAC, source MAC, the next protocol, the data, and then the cyclical redundancy check to be sure that nothing's changed. So we have these things, the two sublayers, creates the frames, manages the unique physical addresses. The unique physical addresses, the MAC addresses. The MAC address, it's a 48-bit hex address. Hex goes 0 through F. And we go, what it represents is we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And this is going to be 10, 11, 12, 13, 14 is what the digits are going to represent. Logical link control multiplexes, controls the conversation, error handling, and flow control can be at this layer. There are, when you look at these things, say, oh, that's handled at some other layer. We had the network layers for flow control. We had the transport layers flow control. Some of these things double up. And you may not have all of the protocols for all of the conversations. If we were, for instance, once we got the MAC address of the destination, we don't really need the IP and all the other stuff to communicate within our own channel access. And I think we've kind of talked about a little bit these a little bit before. Simplex, and I don't have a representation of simplex here, but simplex is one way. So we send and the other guy receives. Half duplex is represented here. We can transmit, we'll say we can transmit and we can receive, but we can only do one at a time. The one lane bridge that we do these things. And that's where the CSMA CD comes in. That we have to wait until this one lane bridge is clear before we can send our traffic. The other one is full duplex. We can transmit and receive. We can do both at the same time. 2-lane highway, interstate highway. Lots of data going on these things, going in the different directions. And again, if we have 100 megabit per second, full duplex, we have 100 transmit and 100 receive. So just by going to the full duplex, we've increased the data rate that our network has. Token ring, carrier sense multiple access. These are a couple of different, I want to introduce, I guess, a couple of new terms here. One of them is deterministic, and that's going to be the token ring. It's going to be deterministic. It means we can determine when we're going to get on because we're going to get the token ring. These two things, and this one down here is going to be probabilistic. Probabilistic because you're probably going to get on the network. I think about these, and I have weird thoughts, as you've probably figured out, as this is in traffic, and a lot of networking can be used, and analogies can be used to regular traffic flow in your car. The packets, the little packets are the individual cars that are going out on the highway, those sorts of things. But in this one, the deterministic is like a stoplight, because if you come up to a busy street with a stoplight, you know that eventually that light's going to turn green, it's going to turn red for the other folks, and you can go. And you can get into the flow of traffic. So when we get the token, we can have access to the media. We can put our packets on the media when we have that. Probabilistic is like a stop sign. You're probably going to get on, but you got to wait until the traffic's clear before you do that. You got to keep checking, is the traffic clear, is the traffic clear. Once it's clear, then you can get into the traffic. If a collision's detected in this thing, then we get the signal here, the collision signal going to all of the stations that say, hey, there was a collision, and we go into a random back off, RBO, random back off, and then go through the same CSMA, carrier sense multiple access. Listen, carrier signal, the carrier sense, we sense the carrier signal in the signaling, the layer 1. Multiple access, everybody's connected there. Wait until the media is clear, and then we send our data, and then listen to see if there is a collision. If there's a collision, we go through the whole process again. The reason the back off is random, if it was a fixed back off, everybody go back and do the same thing and have the collision all over again. Wireless uses collision avoidance. Wireless, in this thing on the left, RTS, CTS. RTS is request to send. The wireless device sends an RTS, request to send, to the wireless access point or the wireless router. And if the data is available, if the media is available, it'll give a clear to send. And then that particular device can send its data, and we get the acknowledgments and all those things. So wireless uses a different type of media access, collision avoidance instead of collision detection for those things. And that's one of the things that makes wireless slower. The other thing that made it really slow up until 802.11n was that you had to acknowledge every data packet with wireless. And now the 802.11n allows acknowledging of multiple packets in a window sort of arrangement like we talked about with TCP last night. The MAC address, let me get this. You probably have seen this, that I will probably insult you sometimes, don't mean to, but some of you have more experience than others. The media access control, if you go to your command prompt and do an ipconfig all, I've got virtual NICs on this one, so I get a whole bunch of stuff. But this one here, the physical address, and this is the actual Ethernet adapter that I'm using. This is the MAC address, the media access control address. This is the device that's going to be put into the MAC address table of the switch, so that when something comes to my address, it's going to go right here. And while we're here, let's go ahead and I want to look at, we talked about the ARP table a little bit, address resolution protocol, and it's not OWL, it's just A. What the ARP table does is tells me, got to find the right network here, this one down here, my default gateway. So I have the IP address and the MAC address, the physical address. The dynamic says that, hey, I figured this out using the ARP protocol. 192.168, another device on this network, and the MAC address. So the MAC address is the one that the information gets delivered. The physical is the MAC address. The NIC ignores a frame not to it. It kind of does and kind of doesn't. Let me do this demo, or try to do this demo. Sometimes it does. Sometimes it works for me. Sometimes it doesn't work for me. How? And don't pay a lot of attention to the commands that I use, because they will come later if you do the Cisco stuff. Okay, so I have one. This is we're going to build the MAC address table. I have a MAC address dynamic on gig 01. That's the router here, and it's sending some traffic. These devices haven't really done anything yet. So what I want to do, I'm going to go into simulation mode. In simulation mode, we're going to be able to see these things one at a time. And I don't know where it's going. Let's just see. We'll just look at this one. So what the switch does, if it does this right, is as the frame comes into the switch, it registers that MAC address with the port that MAC address is on. Again, Dynamics says, I discovered this, the capabilities of the switch. Since it doesn't know where it's going, we only have those two, unless it's going to the router, and I don't think it is. It doesn't know where to go. So it floods the data packets out all of the ports except the port that it came in on. And the red X says it's not to me, not to me, not to me. In this flood doesn't match my MAC address. The difference down here with the hub, and I want you to watch as we do this, is it goes out, and yeah, we would expect it to go out, all of them, and we have not to me, but it is to this guy. So now then we go back into the hub, and the hub's still going to send it out, all the ports except the one it came in on, because it doesn't have a MAC. Now let's see, this one's come into the switch. We'll look at the MAC address table again, and golly, yep, we have it now registered there. So we'll keep going. And you notice when it came back to this one over here, it's got the 52 on it, it went directly out. It didn't get flooded out all the ports because it's in the MAC address table. Try one more here. We go in here and directly down. No flooding because that MAC address is in the MAC address table. When we get to the hub, it's going to go out all the ports because it doesn't have one of those things. The advantage, how does the switch only send it to the device that it's destined for? The MAC address table. First time out, yeah, goes out all the ports. After that, only goes out the port that it's destined for. 48-bit hexadecimal address has two components, the OUI, the Organizational Unit Identifier. And when we look at Wireshark, you'll see that it says it's a Dell or it's a this or it's a that. The Organizational Unit Identifier is assigned to the people that make the equipment, that make the NICs. The unique identifier is the second half. So the first half in the 48 bits, 24 bits, first three hexadecimal numbers are going to be the OUI. The second section, the second three hexadecimal numbers are going to be the unique identifier of it. And these things do need to be unique. If they're not, it gets really confusing because sometimes it gets there and sometimes it doesn't get there. So this works out pretty good for a break time. Questions or comments? So then let's take a break and come back at 10 past. Well, let's keep going. The thing down here at the bottom, and it says EUI64 is Extended Unit Identifier, Extended Unique Identifier, which is used by Cisco. They talk about in the text that it's a 64-bit MAC address. A MAC address is a MAC address is a MAC address. A MAC address is 48-bit. So you can say, okay, for this book, it's the 48-bit MAC address. What it's used for is to create an IPv6 address. And when you see this thing, it's not really all that complex what we do. We take the MAC address and add an FFFE. FF is all ones in binary, and an FE is all ones with the last bit 0. Add an FFFE in the middle hexadecimal. And then they say flip the bit. If it's a 0, the 7th bit, if it's a 0, becomes a 1. If it's a 1, becomes a 0. And we create a 128-bit because we have 48 bits, and then we add the 16 in here. 48. Well, excuse me, 48. We get the 64-bit address, and this is going to be the identifier of the MAC address of the MAC address of the IPv6 when we do these things. So it is something that they do, and as far as I can tell, CompTIA kind of uses some Cisco things, because we'll talk about some Cisco things as we go through the course, but things, protocols, processes, proprietary information. But EUI 64 addressing, the extended unique identifier, and that's the RFC. RFC is request for comments, allows a host to assign itself a unique 64-bit IPv6 interface identifier, EUI 64. In an IPv6 address, we're going to have 64 bits are going to be for the network, the location, and 64 bits are going to be for the individual station. I'm going to try to avoid the host and node. I guess we could use node. So we create the host portion of the IPv6 address by using the MAC address. That kind of ensures that it is unique. This is a process that really isn't used by everybody, but it is available, and and Cisco does use it in the routers when they want to create addresses and kind of assure uniqueness of them. Benefit over IPv4 eliminates the need to manual configuration or DHCP, as in the world of IPv4, and we will talk about those different things. DHCP, you probably already know, Dynamic Host Configuration Protocol, gives you the IP address and other information that you need. What IPv6 does to a great extent is generates its own IP address, so that we don't have to use DHCP for a lot of it. It's going to do its own generation. It's going to check to be sure it's unique, and it's got a whole lot of different options to do that with the 64 bits that are available. But if we use the MAC address is going to help assure the uniqueness, since we know that they are supposed to be unique throughout the world. MAC address separated into 224 bits, one being the OUI, the Organizational Unit Identifier, the first half of the MAC address, and we got another one down here, the first half of the MAC address. Down here, this would be the OUI, who made it? Organizational Unit Identifier, who made it? Who made it? And then over here, the second half is going to be the NIC specific, or the, let's call it the serial, maybe, the serial of this thing. So when we put these things together, they're unique, but we need 64 bits, we only have 48 bits. Each of these is 8 bits. 1, 2, 3, 4, 24, and 24 here, and then we add the 24 in the middle here, right? 16 in the middle here. It's 48 to 16, and we're going to get our 64 bits that we need for the host portion of the IPv6 address to do self-generation. FFFE is inserted between these things, and then the example down there of what one looks like, a couple of examples of what they look like. We still have to put in the front end of this thing the network portion of the address, and we'll look at the network portion and the host portion when we talk about IPv6 and IPv4. But right now we have this special method in order to create these things, and it's in here because it uses the MAC address. The 7th bit from the left is going to be the 7th bit from the left, the count from the left in. 1, 2, 3, 4, 5, 6, 7. Again, if it's a 0, we change it to a 1. If it's a 1, we change it to a 0. We call it flip the bit. So it's going to change a little bit at the front end. The FFFE is one of the big tippers for the EUI 64 addresses. Noticing that the OUI portion, the globally unique address assigned to the IEEE has always been set to 0, whereas the locally created addresses has a 1 configured in them, and that's just kind of what it has been. This starts kind of a new TOPIC era, unicast broadcast, the kinds of information that we can send. Trying to start another machine because I need a virtual machine here in a few minutes to look at some stuff. But IP service, the following 1-to-1, we're going to call it a unicast. Uni 1-to-1. one to all when we send an IP address or an IP message to all of the devices that are on our network, then it's going to be a broadcast address. I'm trying to start Wireshark here. We'll look at a couple of these things. And one to several is going to be a multicast address. Multicast is kind of on a subscription basis, I guess you would say. Multicast, the thing that you will see mostly that use multicast are going to be routing protocols. And how do you get to be a member of the multicast? We install the routing program on the routing protocol on the router, and all of a sudden, yes, it's in that multicast group. But when we look at this thing in ARP that I alluded to a little earlier, is a broadcast. If I look down here, address resolution, target MAC address, who has, now this is going to be local here, there's going to be a broadcast, going to be a broadcast at the layer 2. All F's in the destination MAC address is going to be a broadcast. They don't know who has what, so we don't have the IP addressing in here. Multicast, probably not. Multicast generally going to start with 224, and there aren't any in here. But the unicast, we have a bunch of them going from one IP address to another. The source and destination IP address is going from one to the other. So broadcast goes to everything. Unicast goes to a single device, and a multicast goes to the subscribers. You could kind of in the radio world, you could think about, I guess, that the multicast, maybe if you're a Sirius XM subscriber, you get that traffic. If you're listening to broadcast radio, everybody gets that traffic. And I guess maybe if you have a walkie-talkie, it's going to be a one-to-one. It's going to be a unicast. So the different types of transmissions that are used for these things. And what this down here is trying to show is that the broadcast here goes to everything. The multicast goes to certain select devices. And the unicast only goes to the single, maybe to the web server or to the server that the file server that has your files on it, goes to a single address. This is just kind of thrown in to show that, yes, we do have multicast addresses, and these are multicast MAC that send these things, and they are specific for different protocols. And these are, looks like mostly IPv4 multicast. Insert 23 on the multicast and on down the line, but these are the MAC addresses that would be used for those. CDP, a Cisco proprietary protocol. Spanning Tree, Cisco proprietary, but they have specific addresses that are assigned to them to go to multiple locations. I said earlier that we would look at the frame. This is what a layer 2 frame looks like. And up here, and some of these numbers look a little different. 1568 to 1522 bytes, and up here 46 to 1500 bytes. The original version is 1500 bytes. It's called the MTU. The maximum transmission unit is 1500 bytes of data. And this is bytes, not bits. 46 is low. Anything greater than 1500 is going to be called a giant. And anything less than 46 are going to be called a runt. So we want them between these things. What we do, and we've used the term VLAN, and what VLAN does is put a tag in here that's going to increase the size of this thing that we're going to be able to do. And here we have the 42 to 40. Each of these is going to be a little bit different. We can specify these things too, by the way. But the standard up here is the destination MAC address, the source MAC address. 802.1q is going to be, that's going to be for VLANs. And here the ether type is going to be, and it's going to, this is either going to be, usually, I mean, you could have ARP, IPv4, IPv6. It's the next protocol up that we're going to use. What do we have for these things when we do this? We have the preamble, which is a sequence. The preamble here is a bit sequence, and the start of frame delimiter. These things together, the preamble is a timing operation. It's just a series of zeros and ones to get the frame synchronized. Start of frame delimiter, we started, and one of the reasons that they call it a frame is we have a beginning and an end back here, the frame check sequence, which is going to be the CRC, the cyclical redundancy check. It's going to check to be sure that there's not been any damage en route. So we have the destination address, the source address, the tag here, this is going to be the .1Q tag, the length, the service the destination service access point and the source service access point control, a bunch of control information that gets put into here, and then the data that's going across. And after that, the interframe gap, so that they don't run together. There is going to be a gap, and that's all part of the timing. Layer 2 traffic carried in frames. The Ethernet frames in particular carry the majority of the world's network traffic, because Ethernet frame is going to be the Ethernet is going to be the most popular protocol that we use, and we're going to call it protocol here instead of a topology. And here is, and I think this is the kind of the one out of the book here. We have the data and the payload, 46 to 1500 bytes. The preamble, start of frame delimiter, 8 bytes. The start of frame delimiter is a 1 byte, so the preamble is 7 bytes of ones and zeros in order to synchronize it. Destination address, 6 bytes, the 48-bit MAC address. Source, 48-bit MAC address. The type or length here, and this is going to be, if you go down here, the frame type, 2 bytes. This is the length of the entire Ethernet frame in bytes, or the frame ID can hold a value of 0 to 65,534, but the maximum value is usually less 50. Source destination, and it is typically going to tell us what the next protocol is. You start Wireshark, and after we look at look at one of these things, and then data, 46 bytes to 1500 bytes. The frame check sequence at the end, cyclical redundancy check to be sure that it was not damaged en route. We'll bring this back over to look at, let's go down here and look at find a TCP maybe. A TCP, and here we have the Ethernet, the destination, and again this was Belkin, so Belkin's OUI is 9410. The source is a Dell, so the Dell is 002219, and then the rest of it, you notice, is unique. And then the type here says IPv4. If I had the ARP here, the type is going to be ARP. So the type is the protocol at the next layer up. And then padding, if we need padding so that the frame ends on a 32 byte, is just there to fill up the frame so that we don't so that we don't wind up with a runt of these things. So some questions, I guess, here. What kind of signaling is generally used by Ethernet? Choose the best answer. Baseband, broadband, Ethernet. D, time division. B, let's go with B or A, baseband. Broadband, baseband is, it has everything gets the same, The data gets the entire frequency spectrum. Broadband, if you think broadband, think cable TV, got 150 channels on it, lots of different things on that piece of media. Baseband, what we're seeing in Ethernet, we're sending our data. That's the only thing that goes on there, so it gets the entire thing. You need to set up a long distance full duplex connection between 2 points, but you'd rather not run 2 cables over all the distance. One technology you're evaluating is FDM, frequency division multiplexing, as one of its features. Will it do the job with a single cable? Choose the best answer. And if you read that, what would you say to yourself right now? Would you be able to say yes or no? Maybe. This is one you really would need to know more. Which of the following are valid MAC addresses, and there are, I'll tell you, there are 3. Look at these things. So which are valid MAC addresses here? Which are not valid MAC addresses? Come on. B isn't valid, right? It's too short. It's not got 48 bits. Go 1, 2, 3, 4, 5, 40 bits. And C, because it's got this X in it. Hex goes 1 or 0 through F. So C got the X in it. It's not going to be valid. So actually, C, D, E, D, and E are. How about A, D, and E? C has got the X, not going to be valid. B is too short. A NIC has a MAC address 080027DE3602. What would be the corresponding EUI 64 address? You got B. Remember, you got to flip the bit. That's not a problem, Caleb. You got to flip the bit. You got to flip the 7th bit, so it's going to change the first half. Yeah. Just trying to look at it quickly. FFFE, yep, we got that. So if we've got to change something in the first, then C is going to be the only one that actually changes without going in, and we'll do the calculations later on. How many MAC addresses are in an Ethernet frame header? 1, 2, 3, or 4? 2, the source and destination address, right? How does Ethernet control multiple access? Choose the best response. CSMA CD. So the next section, we're going to talk about repeaters, hubs, bridges, switches, routers, and gateways into this one. And I'll probably try to do some demos. We've done the switch, hopefully a better idea of what a switch does for us. But a repeater is something that in fact repeats the signal. It doesn't amplify the signal. It repeats the degraded signal. It rebuilds it. If it were an amplifier, once we get the degraded signal with a noise, we would have amplified noise along with amplified signal. So the degraded signal gets cleaned up, repeats, regenerates the attenuated signal. It does not do amplification. What happens in copper and in fiber also, we start out with a signal. As it goes down, we get resistance, and the signal strength gets lower and lower and lower. So, and we're going to have, we'll put noise out here. What we have to do is repeat it. Since it's binary, it's easy to figure out, easier, I guess, to figure out what signal. Then we repeat it before the noise overcomes the signal level, and we can go much further. In Ethernet, we have this thing, and I may be getting ahead of myself, called the 5-4-3 rule. Which says that we can have 5 Ethernet segments. And we'll call this a repeater. Here we had a segment and a repeater separated by 4 repeaters, 3 of which may be populated. So we have 1, 2, 3, 4, 5 segments, and we have 1, 2, 3, 4 repeaters. And if each of these is 100 meters, that means that we can actually go 500 meters on Ethernet, which is the true. Each segment's 100 meters, and that's because of the signal degradation and the timing that goes into these things. But 100 meters, figure the furthest that any of these things can go. Aren't common in small office Ethernet LANs. They're not common in any LAN, I don't think, anymore, because we're going to use switches. These things, we used to use repeaters, but that was in the coax days. You may use a wireless repeater. I actually installed a wireless repeater because I was having trouble getting a signal in the basement. But repeaters repeat the signal, and they're going to extend the distance, but they're also going to slow things down a little bit when we do these things. So since most common standards support cable distances up to 100 meters, but they're more common in the campus area and wide area, and they are in cable modem, in the neighborhood, there are a lot of repeaters that repeat the signal there. But in Ethernet, not so much. Hubs, and we've kind of talked about a hub, layer 1 device. And what a hub does is takes our bus here, and we'll put a box around it, put a box around it and shrink it and then put RJ45 connectors on it. So a hub is in fact a bus, and it's a single collision domain. So down here on the hub, all of these guys are in the same collision domain. On the hub, they're all in one giant collision domain here. So a single collision domain for the hub. A layer 1 device connects multiple nodes into a star configuration. It is much more convenient than coax, easier to manage because people can't, undo the connectors and bring the whole network segment down. Collision domain, layer 1 device. Layer 2 devices, we can't extend the network indefinitely with hubs and repeaters. We can create more collision domains as we increase nodes, and that's going to help us. There are other things, and one of the other things was the MAC address table, but in a switch, each of these is a collision domain. So in this one, in my 4-port switch, I have 4 collision domains. And probably going to be full duplex. We have collision domains, but in switches you should not see collisions. And collisions really do slow things down. Create more collision domains, connect to Wi-Fi or a token ring. We need a layer 2 device in order to do that. If we had a wireless access point out here, at some point it has to connect back to the wired network in order to get to the servers out here. We can do that, but at some point we have to bring it back wired to these things. Layer 2 device reads layer 2 information, stores the frames temporarily, and we'll say maybe stores the store and forward will processes the layer 2. So the layer 2 device. The devices that we're talking about here are going to be switches and bridges. A bridge is kind of like the original switch, and its symbol is something like this. What we would have with a bridge is a Ethernet segment over here. We could say a hub. We could have one giant collision domain over here, and we could have another giant collision domain over here. They're still in the same IP network. This side would have the list of MAC addresses over here, and this one would have the MAC addresses over here. If we want to go from A to B, it comes up to the bridge and says, I don't need to go to the other segment. So it's a segmentation thing. If we have C over here, we have C in here. It's A wants to go to C. It comes up to the bridge. It says, oh yeah, C's on the other side. It'll forward the frame to the other side. So bridge, old device, legacy device that is used to segment Ethernet networks into, it creates collision domains. The devices that we're going to have there, layer 2 devices, bridges and switches are going to be there. This is a much prettier picture than the one that I drew, but if we had this one over here, we'll call this one MAC address A and MAC address B and C, D, and E, then this would say A and B is on segment 1, we'll call it, and C, D, and E are on segment 2. If I want to go from A to B, hey, I don't need to go across the bridge. If I need to go from A to D, I've got to go across the bridge, and the bridge will control that. We have 2 collision domains. This is going to be a collision domain, and this is going to be a collision domain in this thing. So it creates collision domains. Switches early on were called multi-port bridges. And sometimes you'll still hear them called multi-port bridges because they create Ethernet segments. They create collision domains. Learning bridge or transparent bridge, and this is probably what I should have waited for to show you how the MAC address table gets created, but it just seemed like a convenient point to do that since we were talking about MAC addresses. But when something goes into the switch or the bridge, was what we just said, we got the MAC addresses listed here, A and C, and then B over here. If it needs to go across the bridge, it's going to do that. If the destination address isn't in the table, it floods, and flood is another Cisco term. Flood means it sends it out, all of them. don't use at layer 2, we don't use the term broadcast, because broadcast, when you think broadcast, think layer 3. The effect is the same, except the broadcast will continue to go out all the ports except when it came in on. The flooding will only do that one time until it finds the MAC address and puts it into the MAC address table. So it floods it out because it doesn't know where to go. That's the only solution. If it's in the table on a different segment from the source, it forwards the frame to that segment, and if the destination is on the same segment, it ignores it and does not pass it to the other side. Translating bridge, and this is, we're going from wireless to wired. Some of these things have they're pretty sophisticated devices. If you think about your wireless router, it's a pretty sophisticated device. It takes wireless signal and converts it to a wired signal, and can go the other way around, the wired signal to the wireless. Switches, layer 2 device, multi-port bridge. And this is a hardware versus software. Bridges use software. Bridges bridge in software. Switches switch in hardware. And anytime that you can do something in hardware, it's going to be quicker than anything that you're going to do in software. It automatically senses the duplex and the speed for the ports, depending on what we plug in. If we plug in a gigabit NIC into a gigabit capable switch, it's going to say, hey, it's a gigabit full duplex. So we plug 100 meg in, 100, it will automatically sense the speed and set the speed of the port. Each port's a collision domain. They're normally going to be full duplex, and then we've already looked at the MAC address table. The MAC address table makes it a very efficient device. Routers, layer 3 device. This is a new addressing scheme. We talked about the MAC address, the physical address. These are the logical addresses, the IP addresses. The IP addresses get us to a location, to a network. The physical addresses get us to an individual device. So we use IP addresses, and we'll talk about IP addressing, I think, tomorrow night. Broadcast goes to all the nodes on the segment. The switch sends or floods the broadcast out all of the ports except the port that it came in on. And if you have that question, be careful about the wording. Not all the ports, but all the ports except the one that it came in on, because it already knows the address there. Routers create broadcast domains. A broadcast domain sends the traffic to all of the devices that are on that IP network. And we have to introduce some things or use some terminology before we've actually done it, which is what we're doing here. This is one of the, just press the I believe button until we do IPv4, and we'll look at more specifically what a broadcast address is. But right now it goes to everything on this side of the router. Routers create broadcast domains. Switches created collision domains. Routers create broadcast domains. Each of these is going to be an IP network, a separate IP network. A broadcast, if we had a switch here with a bunch of different stations on it, a broadcast would go to everything over here. It would not go to anything over here. Routers create broadcast domains. Routers won't forward broadcast traffic. So broadcast domain, IP, collision domain is MAC. Layer 3, layer 2 for each of these things. And then we have here the network path determination, IP logical addressing is what we're going to use in the routers. So it's the layer 3 device, new addressing scheme, the IP address, broadcast goes to all the nodes on the segment. Switch sends or floods out the broadcast out all of the ports, and then the routers create broadcast domains. Normally, specialized devices can be configured, can configure a computer to route. You can configure Linux, any of the Linux versions workstation or server can be configured as a router with multiple NICs. In the Windows world, you have to have a Windows server in order to configure it to route. You can, they're not very efficient. Typically, you're going to use a router device because that's what it's built. Routable layer 3 protocols. These are two terms, there are two terms that sound similar here, which is routable, U-T-E-A-B-L-E, which is going to be IP, and if we had it, still IPX. and routing, which is going to be RIP and OSPF and EIGRP. So a routable protocol, the IP, is something that's going to help us to find a specific location. A routing protocol is going to be used to share information among routers. Gateway, multiple layers of the OSI model. It has lots of meanings. The default gateway is the router that gets us out of the network. Maybe a workstation that's configured to interact with a mainframe computer. So lots of different things. One's a router. Join two networks with different protocols. Join two networks with the same protocol. Join a LAN to a WAN. Different things, different gateways. And a gateway can actually appear multiple layers at any layer of the OSI model. Multi-layer switches or layer 3 switches can work at layer 2 or layer 3. When we install them, they are a layer 2 switch, and they use the MAC address. They have the MAC address table. We can take one of the ports and go into it and configure it, and we just go in and give a simple command, no switch port. And then we can assign it an IP address. It becomes a routing device that can forward routable protocols, can share information with routing protocols, but everything else is still at layer 2. So multi-layer is a layer 2 at birth, can become a layer 3 later on, can be used for routing. If you do Cisco, you do some work with layer 3s, it has some pretty clever things that are available in them. But multi-layer switches, layer 3 switches, can be used at each of these. The advantage of the difference between it and a router is it's going to work in hardware, so it's going to be faster. A router is going to route in software. It's called ASICs, Application Specific Integrated Circuits, to do that. It basically does the same thing with IP addresses that a layer 2 switch did with. So we are now into more questions. Which of the following devices would segment the network into multiple collision domains? A switch would. What about other devices that might do that? A switch that's the one that I want you to think of immediately. A bridge? Absolutely. A bridge would do that. It's not on the list though. What about a router? A router is going to create a broadcast domain. It's also going to create a collision domain because they can't get across there. And then the gateway, which is kind of one of those, yeah, maybe it is and maybe it isn't sort of arrangement. So A, B, and E are going to be the devices that will. Which of the following devices would segment the network into multiple broadcast domains? Choose all that apply. And broadcast is layer 3. Yeah, I figured that one, Cal. D and A, yeah. A router does, and a gateway. And the gateway is one of those kind of like, okay, this could be a gateway, a router can be a gateway. A number of different things can do that. But gateway, default gateway, you probably have heard that one before. A layer 2 switch is essentially a bridge with more than 2 ports, true or false. And we'll go with true on that. You're about to purchase some new network hardware, but you have a couple of old computers you'd like to repurpose as network devices to save a little money. Which of the following would be a useful plan? Choose the best. We want routers or switches? I agree with the routers. How are you going to make it a switch? We can put NICs in it. NIC's a layer 3 device, and a router's a layer 3 device. But we have a difficult time putting layer 2 ports. We're going to configure them as routers. And, oh, by the way, they're going to be pretty inefficient routers because that's not what they're built to do. They're built to do things like we do, you know, to do web browsing, to do documents, spreadsheets, meetings like this, those sorts of things. They can be used, and if you do that, it probably should be in an emergency, or if you've got something that doesn't need the intensity, I guess, of the. The next one is copper media. We're almost up to a break time. We're not done yet, Raphael. It's all going to come together. How's that? This is only day 2, which would be day 1 if you're doing days. Just think about how fast it'd be if you were doing 8 hours a day instead of 4 hours a night. It takes a while. This is not something that you're going to get done a week from Friday and say, okay, I'm ready to take the cert test now. That you're going to have a lot of information, a lot of knowledge, and then what you have to do is take all of that knowledge and kind of put it together into little things. Yeah, 8 hours straight daytime. It's no fun. I do CCNA days. We take an hour for lunch. We start at 8 o'clock Mountain, 9 o'clock Central, and 10 o'clock Eastern. 4 hours lunch, 4 hours exhausted. Yeah, so this comes a little bit slower this way. Don't get discouraged, particularly now. Yeah, the share folder, absolutely I will. And if you want to go back again and watch the videos again, which you may or may not, and you've got the Professor Messer, you got the test banks, and that's when you kind of get into it, or I kind of get into it. And what I will say, and I'll tell you what I usually get the first time I'm through a test bank is somewhere around 40 or a 50. So if you go through the first time and say, golly, I don't know this stuff, don't get discouraged. Just keep studying, looking at the question. Why is that the answer? And that's where that's when you get ready. And when you get sick of answering the questions, it's probably time to take the test. The rest of the night may be a little bit less theoretical and more physical, because we're going to talk about media, copper media, and then we'll talk a little bit about fiber, and then Ethernet standards, and then we'll finish the night out with some lab time. But right now we're going to talk about twisted pair cable standards, twisted pair connectors, RJ45s, coaxial cable standards, and how to troubleshoot the media. This is thrown in the standards themselves and kind of where they're used. What it's really there for is the performance category, because one of the test banks, I saw one that said Cat 7 you need to order, but the only thing that you can't order it by category. The only thing you can order it by is performance standard. What's it going to be? And this is actually a pretty good summary about how it would be connected, what it would be used for different things. So it's available obviously in the share to do those things. Back to what we have is electrical interference is the problem. EMI, electromagnetic interference, is a big issue with copper, because noise induces signals, and signal induces signals, and that's the way transformers work and those sorts of things. And if you've ever, and nobody listens to AM radio anymore, but if you've ever driven under a power line with an AM radio, you get all of that noise. What happens to us with wires that run parallel as we get a noise or a signal even on it, and it gets induced in copper to the other wire that's running. If we can, and we do this by twisting the media, twisting the wires, make it so, and we'll do something like this, where that one's going to cancel the other out to do those things. So what the objective is to reduce. We're not ever going to eliminate the noise, but to reduce the noise that is induced in these things. And we do that by changing basically where the noise signals meet each other in the different wires, and having them reduce each other. So information is carried through a conducting media, closed loop. It has a return path or a ground to go from one to the other. EMI is the enemy. Lots of different sources of EMI. Things like fluorescent lights can induce EMI. If you run, and you may see this sometime, they run the network cable along with the power cables. Not a good idea, because the power cables will induce noise into them. And fluorescent lights really are a big deal. People run them in the ceiling and run the wire because it's the shortest distance. Run it over the fluorescent lights, and then the signal's not very good. So we're going to have lots of different sources of electromagnetic interference. And we're also going to have radio frequency interference, RFI, to go along with other things. Two cables beside each other, what I tried to demonstrate, can cause interference with each other. It's called crosstalk. We also have attenuation. Attenuation is because of the resistance in copper. The reason that we have different distances for different coppers is you can look up in tables what's the distance, what's the attenuation rate of each of these things, how far can we send the signal. So we want to help the situation so that we can better do these things. And the twisted pair is the thing that does that. It makes the signal more EMI resistant with a balanced pair. And what we have, we'll have some pictures here in a few minutes. We have 8 wires inside of a shield or an insulator. It's not an insulator. We'll call it an insulator. And they are twisted in pairs, and we're going to have green, blue, brown, and orange pairs, and they're twisted together. And then the pairs are twisted in order to try to help with this EMI issue. Noise affects the same wire pair. Noise affects both. Some wire pairs, so relative signals the same, affect both of them the same is what I'm trying to say there. So the relative signal is going to be the same, and then crosstalk, we get these things twisting, helps balance out the noise, and then the twist prevents the signals from lining up, and that's what the signal down here is supposed to show. If we get the noise in these things again, if it's the same, they're going to amplify each other. If we do the twist here and we get something like this, and then we're going to get some cancellation. So we want some noise cancellation out of these things, and this is going to be noise amplification if they run parallel to each other. So the twisted pair. And as we go from one category to another, different speeds, the Cat 3 with 10 megabits per second, we're up to, I think, some of the really in shorter distances, really lots and lots of twists. We're going up to around 40 gigabits per second over copper now. But it doesn't go very far. It's not going to be one of the 100-meter ones. We went to 100 megabits per second, and then to 1,000 megabits per second, a gigabit, all in the Cat 5, the Category 5. And the categories define basically what the noise rejection is going to be. So the PVC jacket we see here, and this is not really, this is just one that's in here. We actually can't have stranded or solid. All the ones that we ever used were solid. We used to make our own wire, we'll put our own connectors on it, and they were all solid to do these things. But you can have stranded on these things. This one is it's a big pair. This looks like it's probably going to be a telephone pair, but a telephone cables that goes from one to the other. What you're mostly going to see is something that looks like this, and this is just twisted pair. This is called UTP, unshielded twisted pair. The only thing that's wrong here is they showed that you strip the wire. You don't. You put it in the connector. It's important you untwist them and make them all the same length, and you put it in the connector, and then the connector you drive, and I always say you drive a little nail, a wedge into the insulation, which contacts the copper, and that's the way the signal gets into the connector itself. So this is unshielded twisted pair, and you can see the pair colors. We have the brown, the orange, the blue, and the green. We have one of them's going to be solid and one of them's going to be white with a stripe of that color. So they are twisted, and inside of this, the pairs are twisted together also. This is unshielded because we don't have any shielding on it. We're going to have some pictures of some shielded here in a few minutes. Typically use PVC, polyvinyl chloride. And polyvinyl chloride is because when it burns, it creates a poisonous gas. And I think the chloride portion of this, and as far as I know, it's a chloride. What we want to use is a plenum safe. So plenum, and they are marked on the cable. It'll say plenum on it. You want to use a plenum cable. The plenum is the airspace. A lot of places use above the false overhead as maybe a return air in the air conditioning system. That's the plenum. What happens is if these things start to burn, you don't want them creating this poisonous gas in your system. So we're going to use plenum. They're fire retardant, safe to run through the ventilation systems, and I got this thing the ventilation systems and other plenum space is multiple pairs usually bundled into a single cable. They're color coded, and we have two standards, EIA TIA 568A and EIA TIA 568B. And we're going to look at what each of that is here in a couple of minutes. And the standard is just the order that we do the colors in. This is what the color-coded bundles might look like. Other standards, different methods, 25 pair telephone cable, only 10 solid colors are used for it. So different ones, but we're more interested in our things. And this is the UTP cabling. Some of the different shielding, I have the unshielded twisted pair, has no additional shielding, relies entirely on the twisted pair effect. Foil shielding uses a grounded foil to provide a different, additional EMI shielding. Can be around the individual pair, or it can be around the entire pair bundle, or both. It could be around both. And this one over here in the bottom right, you see that the individual pairs have a shielding around it, and then we have a shielding around the pair bundles here. And that's a braided screen. We can have braided screen or foil. So braided screen uses a braided copper jacket, much like coax does, although the new coax is starting to use foil as around the cable to provide shielding. Can be used around otherwise unshielded cable, shielded UTP, or in conjunction with foil shielding SFTP. Shielded unshielded twisted pair, which is just the shielding around the bundle, or the shielding with the foil. The more shielding, obviously, the better the rejection is going to be of the noise that's going to be in the system. Another kind of, if we want to do this, and it says the CAT table, the category table is in the book on page 73 if you want to look at it. The outer covering, the UTP, outer cover, insulation and core, unshielded twisted pair. Unshielded foil twisted pair here, the outer core, insulation around each of the pairs. We're going to have foil, unshielded twisted pair, foil around the pair bundle, but the pairs themselves don't have any insulation. And then the shielded foil twisted pair, which is going to have with these things. The connectors that we use, RJ11, RJ45. RJ11 is the telephone connector. It has 2 pair 4 wires, and as you see there, typically only use 2 of the wires. If you have 2 lines, you use the 2 interior maybe for one line and the 2 exterior for another line, depending on how they do it. The RJ45, the network connector, is down at the bottom. It has 8 wires, 4 pair. And you can, I said we have this little wedge that we drive into the wire, which is right here. Right here is a copper. When we compress it, it drives a wedge into the wire, and you can see here that they didn't strip it. It goes to the end, drives it into the wire, and creates the connectivity to go to the connectors that go into the little wires that go into the outlet. Making the wire, and if you can make some wire, if you have that opportunity, I'd say go ahead and do it, just so you know what the process is. And it helps you when you get to this thing here, the twisted pair, which color goes where. And the 568A is on the left, and the order is the green and white, white and green. They call the white and green. We always call it green, white, green, orange and white, blue, blue and white, blue and white, and it says blue, but it's going to be orange, and then brown and white, brown. The brown and white and brown are going to be at the end of each of these things. This one, orange and white, orange, green and white, blue, blue and white, green, brown and white, brown, is the one. That's the standard that we use. We always use the B standard. When we do these things, we can have straight through cables and crossover cables. Crossover cables, and we said that we use 2 pair for transmit, 2 wires, 1 pair for transmit, and 1 pair for receive. If we go to a switch or a hub or something like that from a computer, we use a straight cable. which means that we would use the same standard on each side. If we use the 568B, it would be this sequence on both sides of the cable. If we went from a NIC to a NIC, a computer to a computer, a switch to a switch, which is really not a NIC to a NIC, or a hub to a hub, or a hub to a switch, we need to cross the transmit and receive so that the transmit goes to the receive and the receive goes to the transmit. Otherwise, the transmit's going to go to the transmit, and that's called a crossover cable. So it's going to be a crossover. And to make a crossover, you make one with the 568B and the other end with the 568A. If you ever are looking at these things, what do? You swap wires 1 and 3 and 2 and 6. So 1 and 3, we do the green and white. Green and white, 1 and 3, 1 and 3. So we do this here we do this 1 and 3. The orange and white and the green and white, 2 and 6. The orange, those are going to be the ones that actually have the signal. Until we got to the really higher speed gigabits, we only used 4 wires, 2 pair. The original intent was to have 4 wires for the data and 4 wires for the phone system, so that you could have the phone and the data piece of cable. The pairs there, and one I have seen in a test bank a drag and drop as to which colors that you would, what would be the order of the colors for these things. So you have to learn one of them, and then the other one, 1 and 3, 2 and 6, and you got to remember 1, 3, 2 and 6 are swapped. This is another image. Unlike devices are going to use a straight through cable, like to like are going to use a crossover cable. And again, unlike devices, color standard here, we've got the green. Actually, we got the A standard. Both of these are straight throughs, aren't they? Green and white to green and white, orange and white to orange and white. If we had a crossover cable, just move one of these up or down and leave them the same. One side with the 568A standard and one side with the 568B standard. Actually, now we got some crossovers. So straight through, unlike devices. Computer NIC, or a NIC to a switch. If we did a computer to a fast Ethernet connector on a switch, it's going to be a crossover cable. That'll be a like to like. Unlike devices, straight through cable. Like to like devices, we're going to use a crossover cable. And you can see what we cross there. We cross 1 and 3, 2 and 6 to go from 1. And again, in this one, you can kind of see how when you crimp it, you actually drive the edge, and it's a pretty sharp little edge into the insulation, and it goes into the copper activity. It also helps hold it in place. There's a shoulder on it that goes onto the insulation to hold it in place also, so that they don't pull apart. The other thing, and you probably will be asked about these, is this thing called a punch down block. This is what it looks like. What we typically do, another bad drawing, is if we have a room out here, we have a plug here that we plug the computer into, and we run a wire all the way back to the NOC, the Network Operations Center, and it goes to the back side of this thing called a punch down block. And on the front side of the punch down block is going to be an RJ45 outlet that we will then go from there to the switch that guy should be connected to. So a punch down block is, and this is exactly what one looks like on the back side, makes it a little easier to make changes inside of the NOC. So we move this guy, we need to move him to a different switch. All we got to do is change the patch cord here, the jumper cord, the patch cord, to go from it to the different switch when we do those things. We use a punch down tool in order to punch the wires into the punch down block. What it does is it puts the wire, inserts the wire into the punch down block, and at the same time, similar process, scores the insulation and creates a connectivity with it, and at the same time cuts the wire off so that we don't have excess wire. You notice that there's no excess wire on this thing, so they do cut the cable at the same thing. Most most popular standards for touchdown blocks are 66 and 110. The 110 block, a modern telephone, the 66 is the older telephone system. So the blocks, and they used to kind of ask the block numbers, especially which one's the old one, the 66. This is what the front side of the punch down block looks like. We now call it a patch panel. Easier to change the wiring with the patch cords. Intermediate distribution facility of a building or floor, and what that is a switch room, a room with switches in. If you have multiple switches on a floor, you would do that. It would be called the intermediate distribution facility. The main distribution facility is going to be where the network operations center is. That's going to be where your servers and most of your patch panels are going to be. Some of them, the new ones, can do automated switching. This one obviously isn't. We plug the wire in. We would plug the wire in here. Well, this is showing both. We plug the wire into the patch panel, bring it down to a switch maybe, so that we can have that arrangement, make it easier to. RS-232 is a serial connector, and these are the male and the females. It's what's called a DB9 because it looks like a D, and it's got 9 pins on it. If you count those, you've got 5 on one row and 4 on the other. So a DB9 is a serial connector, RS-232. RS-232 serial COM port, although we don't really have those on the new computers. That kind of messes us up in Cisco because we use that in order to connect to the console port of the routers and the switches to do the configuration. Punch down tool, better look at it. Snips cuts the cables to length, and the wire stripper cuts the jacket from the cable. Crimper clamps a modular plug. So crimper clamps a modular plug to the end. This is the punch down tool. I don't have a. Yeah, crimper is going to be on the next page. A crimper does that. A crimper crimps the modular jack onto the wire end of the cable. And the punch down tool places the wires on the punch down blocks, uses a spring loaded to push the wire into place, pierce the insulation, cut the excess length in a single motion. So these things, and you can change the blades, and depending on whether you're using a 110 block or a 66 block, you'll have a different blade on it. This is a crimper, built-in snips and a stripper. Yeah, if you want to use them, and this is just me, I've never had a lot of luck with those. What you want to do, and typically just take a blade and go around, and the stripper is for the outside of the insulation, the PVC, the covering of it, to take it off. You can do that. I always wound up nicking the wire. I always just take a little razor blade and make it, and then you can break it and pull it off. It is a crimper, and this one looks like it's one that'll do either RJ11s or RJ45s. You put the wire into it in the correct sequence, obviously, put it in, crimp it down. It has a little shoulder. The connector has a little shoulder that goes onto the insulation to stabilize it, and then it does the scoring, pushes the little wedges, for lack of a better word, into the wire through the insulation so that you have electrical connectivity. Coaxial cable, the reason is it is coaxial around the center conductor, the dielectric, a shield, and then a plastic jacket on the outside. These things do a really good job of noise rejection. Problem is, the last standard that we used was a 10^2, which is 10 megabits per second. Not going to be very fast. We obviously use it for our cable modems, or cable TV, and those sorts of things, but for data, really not all that used anymore. Two different types of connectors. We have the F connector down here, the one that we typically see with the screw. So we have the F connector, which screws into splitter here or wherever we're going, and then up here the B and C, which has lots of different names. This is what I talked about, the T connector. This is a T connector. This is what a T connector looks like. Connects to, and this would connect to the NIC of the machines, and this would connect to one end of the bus, and then the other end of the bus we keep going, and then we go to another T connector. But BNC, and I've heard it British Naval connector, and on down the line, quick disconnect for things. F connector, the kind that we typically use in our coax for television, cable modem, and those sorts of things. This is just, and I think this one's actually right out of the book, the RG59 and the impedance of each of these things. RG58 was the 10 base 2 down here, the 50 ohm resistor, and this was how big it was, but it's 10 base 2, and then the RG8 was 10 base 5. All of the others up there, RG11, usually only drops for in underground cables, a newer digital cable, common for baseband video and older cable television systems. So the ones at the top, cable TV, the two at the bottom, RG8 and RG58. Testing equipment, different things that we may use. Multimeter to check voltages. A toner probe, what we do with it is put a signal onto the wire, and then we take the receiver to the other end and check the wires to see which one's got the signal on it to go from one to the other. We moved into a new building at ECPI one time. It had a whole bunch of coax running, except it was a whole bunch of coax running. You didn't know what was where when you got to the other end. So we used a toner for it. You plug the signal in, you go to the other end where all of them are, and you check each of the wires to see which one has the, and then you go around and do the same thing, and you make your wire map from there. The cable tester actually tests the cable that we make to be sure that we didn't get the wires crossed inside of the connector, or if it's a crossover, that we did get the wires crossed inside the connector, that we have full connectivity with it. So cable tester tests the cable. Do you need to test the commercial cables? Not usually. Do you need to test the cables that you and I make, especially the ones that I make? So we have some questions about copper. What cables use balanced pair signaling? Choose the best answer. We've got twisted pair. I think that sounds good. What would be... Okay, so the next thing we're going to look at for a few minutes is some optical media. We'll talk about optic fibers, the optical connector standards, and how to troubleshoot optical networks. This is, what are they? Ultra fine, ultra thin strands of glass, and we have light passing through them. Can go a much longer distance. We don't have any interference. We don't have attenuation at the rate that we have with copper. So when we're talking about over here 100 meters, 100 base FX, 400 meters here, 10 kilometers. We were talking in the copper, 100 meters is going to be the standard for that. So 400, 550, 550, 10 kilometers, depending on whether it's multi-mode fiber or single-mode fiber. Multi-mode's a little bit bigger. We can put multiple signals on it. Not going to go as far. That's what we would use inside of our network. Single mode fiber, you can see down there, 9 micron, 9 millionths of an inch. Single mode, single light frequency, basically 10 kilometers. Think of it as long range. A couple of the other distances for the multi-mode, the light source probably going to be an LED. For the long range, the single mode fiber, the light source is going to be a laser. When you're working with these things, laser light causes permanent eye damage, so be careful. Don't look into these things. And they have testers to do these. The fiber costs more to make. The cable itself is more, but not that much more than copper is going to be. An RJ45 connector probably costs about 75 cents. A fiber connector probably costs about $5. A wire tester probably costs, I don't know, $15 or $20. A fiber microscope goes somewhere between $8,000 and $10,000. So in a larger range scale, the tools that we need, much less interference. We don't have EMI. EMI does not affect these things at all. Two types of multi-mode, shorter distances, generally cheaper, less expensive LEDs. Single mode, longest distances, more expensive, uses a laser. And these things do use repeaters to repeat the signal to go the long distances. This is a picture to show you what all is involved in this thing. We have the fiber core. And then we have a cladding out here, 125 microns, and then a coating around it, 250 microns, a tight buffer, 900 microns. A strength member, and this is going to be a Kevlar strength member. And then on the outside, we're going to have the cable jacket, which is going to be the PVC type of arrangement here. You have to strip all of this away to get down to the fiber itself. And what you basically do is glue it inside the connector when we do these things. So just what it is, the outer jacket. This one's a simplified version of the other. And this is the fiber types, the glass core 8 to 10 nanometers, the cladding 125. For the multi-mode, 50 or 62.5 nanometers or microns, microns. The glass cladding, all of it's still going to be 125. The single mode, much smaller, much higher. And these are showing single signal on the single mode, single signal, single frequency. We can still do multiplexing with it. Single color of light, I guess, would be one way to think about that. Down here we have multiple signals on this, multiple colors of light, multiple modes going through it. It comes up to the glass and it gets refracted back in. They call this total internal reflection, which is actually a refraction of this thing. Multiplexing, the different ways, and try to do some pictures here. What we do is break it up into colors, into different colors of the spectrum. The coarse wave, the channels are 20 nanometers apart, 8 channels per fiber when we do that. The dense wave, 0.8 nanometer separation, and this is the transmission over hundreds of kilometers when we do this thing. So it can be broken up into division, wavelength division multiplexing. Different multiplexings we use for fiber here, for copper here. For fiber, we're going to use the light colors themselves, and I think that's the easiest way, and that's what the image shows here. Wave division boosts the fiber capacity. Used on some Ethernet standards, it's more critical for long distance WAN links in the single mode fiber. Multiplexing, we still have the single signal, but we multiplex to put multiple data on the same channel. This one is the different connectors. The original connector over here is a flat, which is the original. Problem was it had an air gap, and we lost some information from it. And then went from there to the physical contact. You notice that it is rounded a little bit. It was designed to reduce the air gap. And then the ultimate physical contact is designed to reduce the wear as we connect and disconnect. And they won't do this all that much. The APC, the angled physical contact, is an 8-degree angle for tighter alignment of these things. And I put a color chart over here, and I actually changed the color of the APC because I did see a question that said, what color is the APC? 62, the flat, are going to be beige, and the PC and the UPC are probably going to be here. The PC and the UPC are going to be blue. Laser optimized or aqua, which is not in the list here. So we use different connectors, and this is kind of the evolution of connectors. When I was doing fiber tech, the flat was what we had. These others have come along, and a lot of the fiber is now machine made, which they can do it faster, better, and all those other. If you look at the objectives, they give a list of connectors, and I've got some pictures of connectors, and I think the FC, the STFC ferrule connector or fiber channel, the ST, the straight tip, the MTRJ, mechanical transfer register jack, and maybe the SCDC is a subscriber connector, are on that list. But those are the ones that you should be able to recognize. The straight tip, the ST, the straight tips, I mean, that's the one that I can always pick out. What can cause issues with the optical? Attenuation, yeah, we can. Bad cable or connector, yeah. Dirty connectors, one of the big problems with these things. Dirt on the connectors is going to impact the ability to send the signals. Bend radius. You have to be careful with the bend radius of fiber. You need to pay attention to it in copper. It's a lot more critical in fiber, because if you get it too severe a bend, then that total internal reflection can happen, and the light's going to escape. Mismatched connection, mismatched wavelength, mismatched fiber type, or a network hardware failure are all things that can happen to fiber to make it not work properly. There are devices to check it. We have an OTDR, an optical time domain reflectometer, fiber microscopes, which you can look at the conductors to be sure that you haven't fractured the glass in it. Just to check connectivities, as a flashlight with a cover over it, a red flashlight with a cover over it that you stick the fiber into. And you guys have probably used them maybe for a sound bar or something like that. It's not like fiber is foreign to you, but these are the things that can happen. So some more questions, and then one more very short module, and then we'll get into labs. You're at a meeting discussing whether to deploy single mode or multi-mode fiber in a new installation. Which of the following arguments should you make? Choose all that. And they all will be 3 that apply. How's that? Yeah, B, D, and F. Did you, speaking of which, Camry, did you get to the share folder after I put the link in there? Or that you can get there? So we have the multi-mode transceivers are less expensive. We're talking LEDs instead of lasers for that. Single mode is better if you use wave division multiplexing, and that is really lots more signal on the single mode fiber. And then single mode works best over long distances. Multi-mode, short distance inside our network, or for our TV, for the sound bar and those sorts of things. I'm just going to go ahead and do this. And which are the small form factor types? And it's going to be the LC and the MTRJ. We can go back and look at those real quick, and then we'll come back to these. So the LC and the MTRJ are small form factors. These others, these are twist-on sorts of arrangement. And this one kind of has a pull action. If you look at it, it's got a little pull the arrow back to release it. These are the small form factor. You can use a coupler to join 2 optical inputs to 1 output, but only if they're the same wavelength. True. And this is one that's kind of, it's kind of counterintuitive, I think. A splitter is a splitter is a splitter. While the optical cables in the closet are outwardly identical, some have green connectors, some have blue connectors. Which is likely true? D. Blue is UPC, green is APC. And we'll go back and look at that one. And this little table here, green is APC, the angled, and blue is the other ones. And maybe you'll see flat, but flat are actually pretty old, not all that popular anymore because of the air gap, and you lost signal with the air gap. You've set up a new fiber optic network using existing fiber that's been laid on your campus. You need SFP plus transceivers to plug into it. But you see there are both duplex and bidirectional transceivers available. Which should you keep in mind when planning your purchase? Choose A, bidirectional, fewer fibers. I'll go back to these connectors again here. You notice that they, except for this one up here, these things go in pairs. One of them in the RJ45 in the copper, we don't see it that we have 2 wires are transmit, 2 wires are receive. In these, it's kind of obvious. We have one of them's a transmit and one of them's a receive. So we have 2 connectors on these things. But the bidirectional coax, a bidirectional here, would allow a single piece of coax. Bidirectional require fewer fibers but are more expensive for fibers. This is the last module, and I kind of promised it will be relatively short. We'll finish that. You'll have just about an hour, maybe a little less, but about an hour of lab time available. We can talk about legacy Ethernet standards, current Ethernet standards, specialty Ethernet standards, and how to configure advanced Ethernet. So the legacies, the 10 base X, 10 base, 10 megabits per second over coax or twisted pair, depending on what the end was. 10 base 2, 10 base 2 there in the insert. Maximum cable segment was 185 meters, 607 feet. And the meters are typically what you're going to see. The cable length, the minimum cable length, 0.5 meters. Yeah, you do have minimum cable lengths for these things so that you don't, an antenna theory would be an infinity or a short or that it would see. So 10 base 2 was called ThinNet. It was a physical bus, the one we've talked about. We talked about the 5-4-3 rule, 5 segments separated by 4 repeaters, 3 of which may be populated. 10 base T, physical star, twisted pair network, initially used in hubs and bridges, half duplex, had collisions, single collision domains. Today we use them in switches. 10 base, well, probably not 10 base, 100 base T, 100 base TX, 1000 base, not. Although you can have, and if you notice on a switch, it's going to be a 10, like here, when the green is 10-100, 10-100, and it should say 1000. I can fix that. 1000, which means that since it's auto sense, when we plug it in, it's either going to connect based on what this thing is going to be connected, either 10 megabits, 100 megabits, or I tried to get some that talked about here when the orange LED is on, the port is being connected, but no data is being transferred. When the orange LED is blinking, data is being transferred. When the orange LED is off, you may or may not have, and this one, the one that has 2 lights has a green LED. One of them is going to be what's called the link light that we have successfully, we got the right kind of cable. We've successfully plugged into the switch. The other one's going to blink when we have data transfer, and it's going to blink a lot. This one over here just has a single light. So different NICs are going to have different arrangements, but this would be what you would use to answer one of the CompTIA questions for this. Fast Ethernet, 100 base, Fast Ethernet, 100 base TX for twisted pair, 100 base FX for fiber optic to do these things. And the distances here obviously are going to be different. The TX, the twisted pair, the copper, 100 meters. The FX, multimode fiber, half duplex, 412 meters. Full duplex, 2,000 meters. So we're going significantly farther with fiber, and that's one of the things that's made Ethernet, the Ethernet standard, more popular with others. It's actually why it's used in the WAN technologies now. Hubs and bridges increasingly replaced by switches, and hopefully you'll never see a hub or a bridge. Switches, probably don't even cost any more at all, but they're certainly worth it. Auto negotiation of link properties, we talked about that. It will automatically negotiate either the speed and the duplex based on whatever the capability is at the other end. The indicators, and I just put this one in here, the Ethernet switch with the speed indicator lights. If we plug it in 100 megabits per second over here, 10, so this is a 10-100. If we plugged in a 100 meg NIC into here, it's going to negotiate 100 meg. If we plugged a 10 meg NIC in here, it would negotiate for 10 megabits. The gigabit Ethernet, and again some tables in here, the 1000 UTP Cat 600 meters. Let's see, the fiber here, we're going multi-mode, 550 meters, 5 kilometers, depending on which sort of arrangements that we have. What I was trying to get to is the gigabit can still go 100 meters. The 10 gig, depending on whether it's unshielded twisted pair, Cat 6, or foil UTP, Cat 6A, can either go 55 or 100 meters. And I think this is one that shows that the shielding makes a big difference in the copper itself. Twisted pair, 1000 base T, 4 wire pairs. TX, 2 pair, and they're going to have a specification. The newer copper twisted pairs use all 4 wires, and especially when we get to the 10 gig, you have to use all 4 wires in order to get those kinds of data rates. The RJ45 and SC connectors, the RJ45 here and the SC connectors down here, the fiber connectors that can be put into these things, or the fiber connectors here and the RJ45s at the top. Another table, the max supported distances and all those other things. And just in case anything happens, I just heard a big boomy. We're having some pretty big thunderstorms. The last time we had that, I lost power. If that happens, just go ahead and do labs. And I'll get back on as soon as I can. But anyhow, the different category table, the maximum supported standard, and then the distances that are available. The configuring the advanced Ethernet options. Let me see if I can. And this one is what I want to do is the advanced standards. We can go in and make some configuration changes to the adapters, the properties, and then the advanced. Here we go, the advanced. Different things that can be configured here: energy efficient Ethernet, auto disable, gigabit is disabled because it is a gigabit connector, flow control, green Ethernet, jumbo frames, to configure it to accept jumbo frames. There are instances where we want to do that. The network address. This network address is, we can actually go in here and type in a new MAC address if we want to do that. And we're not present, we'll use the one that's on the that's already on the NIC itself. So this is shut down and wake on LAN. Disable wake on LAN would wake it up if we had network activity. Those are something we can send a signal magic packet in to be able to start up a machine, maybe to do an update in the middle of the night. Speed and duplex, auto negotiation. We can go in and configure it if we want to, gigabit. We got 10 meg, half duplex, full duplex, auto negotiation. We're going to leave it as auto negotiate. So the advanced features are the things. Wake on LAN is going to, that's where we would send in to wake it up in the middle of the night. But we can make some configurations if you really want to. If you configure the speed and duplex to be anything but auto, you've got to configure the switch. Even if it will do an auto pick it up, it's still considered a misconfiguration. Ethernet options in those. So we now come up to our